In this video, we will review the approach to use the initial rate method in finding the rate law for a particular reaction. We're also going to extend our understanding by seeing a more tricky example, although in the end, when you see what the result is, it isn't actually that more tricky. So here we have a reaction between ethene and ozone to form formaldehyde, or also known as methanol, and oxygen gas. We're trying to determine the order of the reaction with respect to the ethene and the ozone. As in any initial rate method, it's important that we keep between two experiments a concentration of one of the reactants constant, and then we change the other and see its impact on the rate of reaction. So if we compare experiments 1 and 2, you can see that we keep ethene's concentration constant, and we have the ozone concentration. So then we write out, in a sense, a modified version of the rate law. So it would look something like this. Rate 1 divided by rate 2 is equal to the ozone concentration 1 divided by the ozone concentration 2. Now, as I've mentioned before, I encourage you to put in the numerator those values that are larger concentrations, larger rates. It makes the math easier as you're going along. Now you'll notice that I didn't include the symbol for K, nor did I include the symbol for the concentration of ethene, as those are constant. So we can immediately go to a simpler version of this rate law divided by rate law. Now just to remind you, what we're trying to find out here is what is the exponent m for that ozone. In other words, what is the order of the reaction with respect to the ozone. The next stage is to simply plug in the appropriate values. So I plug in the rate 1 and rate 2, and I plug in the respective ozone concentrations for each of those experiments. Now, because we're trying to determine an integer exponent, we really don't need to worry about significant figures in doing this determination. So in other words, dividing the two rates, I essentially get a value of 2. And then over here for the concentrations, of course, I'm trying to determine the exponent m, and I divide the top concentration by the bottom concentration, and once again, essentially, I get a value of 2. So then, of course, we're trying to determine what the value is for that exponent. It should be pretty obvious that the value for the exponent m here is simply equal to 1. So now we have found the order of the reaction with respect to the ozone. Now we turn our attention to the ethene. The idea here is we want the concentration of the ethene to change, but we would hope that the ozone's concentration would remain constant between two experiments. In this case, that's not the case. However, this is not a problem because we already know what the order is with respect to the ozone. So for instance, if we compare experiments 1 and 3, and here I write a modified rate law. I don't include the symbol of K, but I do need to include the symbols for the concentrations of ozone, because indeed the concentration of ozone changes from experiments 1 and 3. Again, what I'm trying to find out here is what is the exponent for the ethene component. In other words, what is the order of the reaction corresponding to the ethene? I already know what the order of the reaction is with respect to the ozone. So now I plug in the appropriate values. The two different rates of reaction, rate 1 and rate 3. I plug in all the respective concentrations. And just to highlight, what I'm trying to solve for here is what is the exponent n? I already know that the concentrations for the ozone have the exponent 1. Once again, when I do this math, I can use basic integers because I'm looking for an exponent that's actually an integer. So dividing the rates, essentially I get a value of 8. Dividing the concentrations of ethene, I get a value of 2. So that would be 2 to the n. Dividing the concentrations of ozone, I get a value of 4. Now I divide both sides by 4, and essentially I end up with the following equation. 2 is equal to 2 to the n. Therefore, it should be clear that the value for n, once again, is simply 1. So the order with respect to ozone is 1. The order with respect to ethene is 1. The last thing that we need to do in this analysis is to determine the units and the value for K. So here is our rate law. What I'm going to do is rearrange to solve for K, and then I'm going to pick one of the experiments, in this case experiment number 1, and plug in the respective values. You notice that I did not bother writing the exponent 1 for the ethene and the ozone because it's understood that it must be 1. So now plug in the values, and I think it's very important that you include the units so that you can end up with the correct units at the end of the calculation. This time we also need to pay attention to significant figures. So I do the math here and I find that it equals 1.0 times 10 to the 3. I've included the units so that you can see that essentially what happens here is that molar cancels with molar, and therefore we end up with molar to the -1 and seconds to the -1. So the units would look like this. These are the units and the value for K. Note that the units are entirely consistent with what we would expect for an overall second order reaction. So just to highlight here, the overall order is equal to 2, and that is entirely consistent with those units. I hope you have found this video helpful in reviewing the process to determine the rate law using the initial rate method, and also seeing a slightly more tricky example, which once you know how to do it, really isn't any more tricky.